During the first 6 months of 1965, MSC-directed activities produced notable gains in the Gemini and Apollo programs. In the Gemini program, the years since the last Mercury spaceflight in May 1963 had been spent in designing, testing, and filling the hardware pipeline, bringing the second-generation Gemini spacecraft closer to operational capability. In the early months of 1965, these efforts began to pay off in a succession of events that would have meaning for Gemini, Apollo, and all future manned spacecraft programs. In January 1965, the final unmanned Gemini flight, GT-2, provided the necessary flight verification of the onboard systems and the heat shield. Also in January, the last of the Gemini spacecraft systems were in manned flight qualification testing. The spacecraft recovery system successfully completed its 10th and final manned qualification drop test, February 11th. By mid-March, the ejection seat system had completed flight qualification aboard an Air Force F-106 aircraft and under simulated pad abort conditions. The ejection seat system was subjected to more than 100 qualification tests before being considered ready for the first manned flight. The Gemini personal parachute, as a subsystem of the ejection seat, passed a separate qualification program consisting of over 36 drop tests. By late March, Gemini 3 was ready. Astronauts Virgil Grissom and Jan-Jun prepared for the first manned Gemini flight. On March 23rd, 21 months after the last Mercury flight, GT-3 lifted from Cape Kennedy's Launch Complex 19. During their 4-hour, 3-orbit mission, the astronauts evaluated the ability of the spacecraft and its systems to perform longer duration missions. They accomplished a major spaceflight first by maneuvering their spacecraft in preparation for future rendezvous missions. They initiated the use of the Gemini spacecraft as an orbiting laboratory, and they executed the first manned, controlled lifting re-entry. Spacecraft 4 arrived at the Cape on March 4th. It had completed its manufacturing and checkout phase 10 days ahead of schedule. Preparations for the GT-4 mission were accelerated in all areas. The extravehicular garment received more than 200 hours of around-the-clock testing before it was considered flight qualified. In this test, pressure inside the vacuum chamber represented an altitude of 180,000 feet. The temperature inside the cold frame was minus 300 degrees Fahrenheit. The suit successfully passed all environmental tests. Samples of the extravehicular suit's thermal and micrometeoroid protection layer were tested in MSC's hypervelocity gun. The material successfully stopped a glass pellet traveling 20,000 feet per second. Performance demonstrations were also required of such items as the Gemini Impact Protection Visor. The 7-pound weight was dropped from a height of 4 feet. The visor is made of polycarbonate plastic, one of the most impact and shatter-resistant transparent materials known. Mission preparations were also underway at the Mission Control Center, Houston. The center received its operational shakedown in monitoring the GT-3 mission. For GT-4, it was fully activated, ready to serve as the worldwide monitoring and control point for all future NASA manned space flights. Cape Kennedy, June 3rd, launch day for GT-4. Command Pilot James McDivitt and Pilot Edward White entered the elevator and rode it to the White Room at the top of the erector. The crew entered the spacecraft and the hatches were sealed. At 10:16 a.m. Eastern Standard Time, June 3rd, Gemini 4 rose from pad 19. Four days later, after completing 62 revolutions of the Earth for a new United States spaceflight record, astronauts McDivitt and White were returned to the primary recovery ship, the aircraft carrier WASP. The GT-4 mission had been accomplished with outstanding success. Although the flight crew did not succeed in an attempt to approach the burned-out second stage of the booster, much was learned about rendezvousing with another object in space. During EVA, the extravehicular activity portion of the flight, astronaut White proved that man could control his motions in space by using either a maneuvering unit or a tether. He showed that man could exist and perform useful work outside the protective environment of the spacecraft. The astronauts' ease of mobility around the spacecraft without suffering any ill effects provided valuable data in advancing extravehicular activity as an operational space technique. EVA will be used on future Gemini flights for the retrieval of experiments from portions of the spacecraft outside the cabin. In the Apollo program, the technique will be practiced as an emergency crew transfer mode between orbiting command and lunar excursion modules. A total of 11 experiments were conducted on Gemini 4, including synoptic weather and terrain photography. In the area of mission planning, task and duty schedules, which had to be precisely defined and executed during earlier short-duration space flights, were found to be more flexible during Gemini 4. Throughout the flight, valuable experience was gained in on-the-spot mission planning, which will take advantage of flight opportunities as they occur. Of medical importance was the fact that preliminary post-flight examinations of the astronauts showed no physiological effects that would prevent man from performing effectively on even longer space missions. The Gemini spacecraft itself proved to be a stable platform in which man can live and work to acquire valuable scientific data. Overall, the Gemini 4 mission increased confidence that the Apollo manned lunar mission will be accomplished within this decade. The next manned flight is Gemini 5, an 8-day mission scheduled for launch in late summer. On June 1st, Spacecraft 5 was subjected to a series of manned altitude tests at the McDonnell plant in St. Louis. Gordon Cooper, Prime Crew Command Pilot, and Charles Conrad, Prime Crew Pilot, functioned as integral test components. The tests validated the performance of the environmental control system and other key systems during simulated orbital flight. The spacecraft met all performance criteria. Spacecraft 5 will use two new onboard systems, a rendezvous radar and fuel cells. The fuel cells, instead of batteries, will furnish primary electrical power for the spacecraft. Fuel cells combine hydrogen and oxygen reactants to generate power. They offer a weight advantage over batteries in long-duration flights and will be essential to the Apollo manned lunar flights and other extended missions. Spacecraft 5 will also carry a 76-pound radar evaluation pod, which will be ejected during the second orbit. The flight crew will later attempt to rendezvous with the pod. The exercise will be useful in preparing for the full-scale rendezvous operations that will take place on the GT-6 mission. The flight crews for GT-6 were announced in April. Walter Schirra will be the Prime Crew Command Pilot. Thomas Stafford will serve as Prime Crew Pilot. Virgil Grissom and John Young will form the backup crew. Primary mission of the GT-6 flight will be to rendezvous with an Agena target vehicle. At Lockheed Santa Cruz Test Base, the Agena vehicle for the first Gemini rendezvous mission was test-fired for the first time as a completed unit. Following de-erection, the vehicle underwent a detailed systems inspection and buy-off. In May, it was packaged and shipped to Cape Kennedy to await an October launch. Rendezvous techniques developed with Agena will help perfect the docking capability necessary for Apollo lunar missions. In April, the Gemini 6 launch vehicle was erected in the vertical test facility at Martin, Baltimore. The event marked the first time the test facility had been used to its full capacity for handling 2 launch vehicles at one time. The companion vehicle, GLV-5, completed testing in early May. GLV-6 was scheduled for test completion and shipment to the Cape in late July, continuing uninterrupted hardware delivery in support of an anticipated 60-day Gemini launch schedule. Paralleling events in the Gemini program were advances in Apollo spacecraft development and manufacture. At the Downey, California plant of North American Aviation, Apollo manufacturing status was rated in the first mating of Spacecraft 009 modules in preparation for final equipment installation and factory checkout. 009 will be the first spacecraft to be flown aboard the first Saturn 1B. The flight is scheduled for early 1966. One of the primary objectives of the 009 mission will be to test the structural stability and heat dissipation characteristics of the command module heat shield. A boilerplate spacecraft fitted with a reinforced aft heat shield of the 009 design was tested in the Downey pool. The drop simulated the most severe conditions of velocity and impact angle anticipated for Apollo. In an earlier water drop test, the 009 heat shield design had failed under similar impact conditions. The fix proved successful, resulting in no delivery slippages. Following water drop verification tests, the shell structures for the 009 heat shield were shipped to the Avco Corporation, Lowell, Massachusetts, for the application of heat shield ablation surfaces. After the fiberglass matrices were bonded to the heat shield shells, they were machined to dimensions slightly above final size. This facilitated filling with the ablator material. When the ablator material had cured, the surface was again machined, this time to critical dimensions. Concurrently, North American's Rocketdyne Division, Santa Susana, California, completed tests of heat shield temperature sensors. The sensors are placed at the heat shield bond line under the ablator material, where they will report re-entry temperatures. In this test, a sensor was installed in a section of heat shield structure, and the sample was heated to over 4,000 degrees Fahrenheit. The sensor remained intact and continued to function after the heat shield structure had disintegrated. North American continued development testing of the 009 Command and Service Module reaction control subsystems. In March, the Rocketdyne Command Module RCS breadboard system was subjected to sea-level steady state and pulse firing tests. The firing sequences were tape-controlled to simulate pre-entry and entry mission duty cycles. The Marquardt Service Module RCS breadboard system was also tape-programmed through a simulated mission cycle. The hypergolic-fueled engines are controllable from a maximum one-time burn of 500 seconds to a pulse duration as short as 20 milliseconds. RCS development is proceeding to meet the 009 launch date schedule. Continued performance tests were conducted on Apollo fuel cells by North American, the contractor Pratt & Whitney, and MSC. The series included duration performance runs in which the fuel cells produced electrical power for more than 1,000 hours, more than double the requirement for a 14-day lunar mission. The tests help prepare the way for early manned flight qualification. In May, North American installed 3 operational fuel cells in Apollo House Spacecraft number 1. This was the first time that fuel cells had been installed in Apollo spacecraft hardware. The cells will be used to test systems installations and interfaces in the North American Permanent Development Fixture. Also in May, Production Guidance and Navigation Subsystem number 8 was received at Downey from the prime contractor AC Electronics, Milwaukee. The unit will be installed in House Spacecraft number 1 to aid in subsystem integration checks. Changes in the Apollo pressure suit design were evident in the latest developmental suit delivered by Hamilton Standard. The suit entered an extensive performance evaluation program, including crew couch fit checks, in an Apollo mock-up. The pressure garment exhibited improved mobility characteristics as compared with the older suit on the left. The new bubble helmet worn on both suits provides a greatly increased visibility range over earlier models. The prototype Block 2 lunar mission pressure garment will evolve from this design. Other Apollo development work was evident at the Army's White Sands Missile Range, New Mexico. On May 19th, NASA and contractor personnel conducted the latest in a series of flight tests designed to qualify the Apollo Launch Escape subsystem for manned Saturn launches. Unmanned Command Module Boilerplate 22 was the flight article. The purpose of the test was to determine the performance of the launch escape subsystem under high altitude conditions at approximately 112,000 feet. 5 seconds after liftoff, the Little Joe 2 launch vehicle began an unprogrammed roll, apparently the result of a control fin servo valve failure. The roll rate increased until it imposed loads which surpassed the structural limits of the vehicle. Vehicle disintegration triggered the abort sequence at 12,000 feet. Engineers termed the test a bittersweet success, for while not all mission objectives were attained, the launch escape subsystem performed perfectly under conditions which far exceeded the limitations of Saturn V emergency detection equipment. The test did not affect Apollo development schedules. Missed data will be obtained on a later mission. On June 29th, White Sands was again the scene of a launch escape subsystem test. Boilerplate Command Module 23A was the test article. The primary objective of the test was to determine the performance of a boost protective cover and a canard turnaround system under pad abort conditions. The test was successful in all aspects and paved the way for the final launch escape subsystem abort test, in which a flight weight command module will be used. At MSC's nearby White Sands test facility, a major milestone was achieved on February 5th with the first successful firing of a flight weight service propulsion subsystem. Through the end of June, the subsystem had completed a total of 8 test programs designed to establish performance benchmarks. Continued success of the fixture's initial firing program will lead to ground testing for upcoming spacecraft missions. At the nearby LEM engine test area, the Grumman HA-3 test rig was installed in the newly completed ambient pressure stand. The rig contains heavyweight tanks, tubing, connections, and fittings for initial firings of the LEM ascent engine. The first firing of a Bell Aerosystems ascent engine took place on April 15th. It provided another milestone in moving Apollo closer to operational capability. In preparation for other LEM development work, Grumman Aircraft continued final assembly and checkout of ground test vehicles in its newly completed White Room at Bethpage, Long Island. The vehicles are slated for testing in high-altitude simulations at White Sands. In February, a full-scale LEM mock-up was placed on a simulated lunar landscape constructed at the Manned Spacecraft Center. The mock-up is being used in time and motion studies relating to lunar surface mobility characteristics. The studies are being aided by the use of a 6 degree of freedom simulator. The device creates the effect of lunar gravity by counterbalancing the test subject's weight to 1/6 that of his Earth weight. To provide Apollo astronauts with an idea of the geological formations they may encounter on the moon, geology classroom sessions were held on several of the lava flows in the Hawaiian Islands. The erosion-free quality of the Hawaiian flows is believed to most closely resemble volcanic surface features which may be found on the moon. The training will help the astronauts select the most meaningful samples of lunar composition to aid in the study of the Earth-Moon system. In June, the scientific capability of manned space missions was broadened by the addition of 6 astronaut trainees from strictly scientific backgrounds. Represented are doctorate degrees in geology, medicine, and physics. This brings to 34 the number of astronauts in training at the Manned Spacecraft Center. Although MSC has the overall responsibility for manned spacecraft programs, it depends on the support of other NASA centers to aid the accomplishment of these programs. An example is the use MSC makes of the 18-station worldwide tracking network maintained by NASA's Goddard Space Flight Center, Greenbelt, Maryland. Goddard gathers the data and relays it in real time to the Mission Control Center, Houston, making possible split-second mission control and planning. Manned Apollo launch operations will be handled by the Kennedy Space Center. The center had 2 milestone events which will influence the success of Apollo missions. One was the completion of the steel framework for the Vehicle Assembly Building, VAB. The 525-foot-high structure will be used for checkout and assembly of Apollo Saturn V vehicles. The second milestone was the functional testing of the first Apollo Saturn V crawler transporter. The 6 million-pound tractor will move assembled space vehicles from the VAB to the launch pad. Apollo launch vehicle development is proceeding under the direction of the Marshall Space Flight Center, Huntsville, Alabama. On May 25th, the Marshall-developed Saturn I launch vehicle, SA-8, completed the 9th successful Saturn I flight in as many launches. Experience gained from the Saturn I program is finding direct application in the development of the Saturn IB and Saturn V vehicles. SA-8 placed this nation's second Pegasus meteoroid detection satellite into a near-Earth orbit. In orbit, the Pegasus, also developed under Marshall's direction, spread 96-foot wings to measure meteoroid activity in space. The measurements will help determine the design of spacecraft hulls to provide maximum meteoroid protection for flight crews. Research programs directly aiding the manned spacecraft effort are being conducted at NASA's Langley Research Center, Hampton, Virginia. These include studies into the use of frangible tubing for spacecraft shock attenuation, LEM and command module rendezvous techniques, spacecraft buffeting tolerances as determined in transonic wind tunnel tests, and the performance of experimental landing systems. NASA's Ames Research Center, Moffett Field, California, is engaged in a number of manned spacecraft-oriented investigations, including the study of sea urchin egg behavior under weightlessness. The study is aimed at detecting possible changes in cellular reproduction processes resulting from the weightless environment. On March 24th, NASA's Jet Propulsion Laboratory, Pasadena, California, relayed live TV coverage of the dramatic termination of the Ranger 9 flight on the surface of the moon. The spacecraft returned the greatest quantity of data of the 3 Ranger missions. The data generally confirmed the findings of Rangers 7 and 8, that there are suitable landing areas which appear capable of supporting the weight of a lunar excursion module. Detailed knowledge of lunar topography and surface bearing strength will have to await the findings of the Surveyor program, also the responsibility of JPL. Surveyor spacecraft will land on areas selected as possible manned landing sites. They will analyze the surface conditions and radio their findings back to Earth. By June 30th, the first flight test soft landing Surveyor vehicle had entered final systems testing. It will be delivered to Cape Kennedy for a year-end launch. Significantly, the cooperation and progress experienced in MSC programs during the first half of 1965 marked the midpoint in the United States lunar landing timetable. These events represented important milestones both in the Apollo program and in furthering more ambitious manned spacecraft projects for the continued exploration and utilization of space.